All right, let's get right back into it. So, first I should introduce myself. My name's Pat. If you've never watched this before, I work at a company called Oneflare in Sydney. We're a startup, a pretty cool tech startup, and we do these streams a couple of times a week just to show off what we're doing in R&D and stuff. So, if you're interested, check out our blog, oneflare.io. We'll paste some details in the chat later on with where you can get resources and stuff from. But let's just get straight back into it. So last time we were making our Gameboy emulator and we got to a point where some stuff could be displayed to the screen. So I'm just going to build it here. If you don't have the code, or if you want to continue from now, let me paste the code in there. We have it on GitHub. So one moment. Probably should have prepared this before starting the stream. Here we go. You can access it just from there. If you need to get the code, I might add it as an overlay actually. Okay, let's see what this looks like. Adding it in real time. Where is it there? It's not super helpful, is it? I think I need the black background. Let's see. Color one. Black. Okay. That's awful. Maybe if we do both colors black. Okay, that's a bit better. Alright, so there we go. So that's where you can grab Shell's face. I think you might have an in here. But yes, we are always hiring. So just check out oneflare.io. But I think you've probably got an in already, so don't worry too much. That's the little URL to get to the code that we've written so far. So,
what is that extra window?
is it actually showing up on the stream?
It's gone now. Huh? It's gone. Yeah, the window. There was one extra window there.
Oh yeah, where did that go? Because I kind of need that. Oh, here it is. It's at the top. I kind of really need that. There we go. So that's what we're actually trying to display. Which is just a horizontal line, but using the color palette. So, I've added one more line here, which is become first responder, just after where we actually load the ROM, and I'll get to that in a moment. But we just need to make sure that this window becomes first responder, because it's going to be it's going to be like accepting, key inputs and stuff. We can't have the STL. Oh no, we can have the STL window do it. Let's just leave it there for now anyways. So, back to Game Boy Core. So we've got this load ROM method, which we're calling here. And we're calling it from here. And we're just loading that simple ROM CPU instructions. And all that's going to do is just run through most of the opcodes that we need to be able to emulate a Game Boy, and then it's just going to spit a result out to a memory location. We just inspect that location, and then we'll know if the opcodes have been implemented correctly or not. So then we're calling load ROM. Load ROM is doing all of our prep work here. It's calling this turn on thing, which is zeroing out the registers and all that good stuff. I realized what might be fun is if we actually knew what was in each of those registers, because we're going to need to know that to figure stuff out. And I suppose building all these dev tools now, these debug tools now, is going to be way more helpful. So why don't we do that? I'm thinking what we'll do is we'll jump into the storyboard and we'll jump into our main window. So when we launch the app, we're given two windows, the actual main window and then this little SDL window that we spawn. And so we can do kind of whatever we want with this main window. So if you've done any iOS programming, this is very, very similar. Just everything's NS instead of UI. Alright, we don't have a custom class for that. We don't have a custom. Where's the relationship? View, no, view controller, cool. So this view controller owns that view. So if we think about the what we want to display here, we probably want to display the registers, the stack pointer, the program counter, and maybe the cycle or something like that. So if we look at the CPU manual, I hope that's not jumping around too much. If we go to, where is it? No power node, interrupt, IO registers, program counter, stack pointer. So we need program counter, stack pointer, and then here are the registers here. So A, F, B, C, D, E, H, L, S, P, and P, C. So that's really all we need to display in our little debug thing, just so we know constantly what's going on. So we'll just put them here. Now, so it's good. Come on, Xcode. It's just pinwheeling. Thank you, Bakara. So it's actually in the code. If you go to this URL here, you can download that in the resources directory. It was something that was written by written by a group of people. I actually printed out a copy of it ages ago, with names such as Pan of Anthrox, Gabby, Cooper, Bowser, and so on. All these old like Game Boy hackers. Anyways, they kind of figured out all this stuff, put it together in a little document, improved it over time, and this is like the final version, which I think was written in like 1999. There you go. Is that right? Maybe. But yeah, all of those instructions are documented in there, and that's in the resources directory. Bakara. So what was I doing? Right, I wanted to display this. So let's get something that we can use to display each of these registers. I guess, probably a label would make the most sense. But then we have to do like a million labels. What should we do? I guess we can just do text, but I don't want to do text. Now let's do labels. All right. So we'll go registers, and then A, F, B, C, D, E, H, L, S, P, P, C. I don't want to do this in a tedious way, but I think I'm going to have to do it in a tedious way. What do you think? Maybe there's a different way of doing it. Let's have a look. Let's have a look. See, if this was iOS, I'd just use a table view, right? Because table views are everything. Maybe that's what I can use here, table view. Grid view. No, but then I need a view for each item in the grid.
Your favorite stuff.
My favorite. Yeah, how'd you know? I just love stack views. They're so useful. The worst view. They don't do anything. Rules. Tool editor, collection view. See, collection view would make sense. You know what, let's just do text for now. Let's just do a two labels. Actually, we'll just do a big. We'll just do a big old label. There we go. That's all we need. All right. Yes. Create a reference to this. And we'll just call it debug output. Perfect. All right. So herein lies the problem, though. Self.debug output.string equals hello world. So this should work fine. Obviously, pump up that mic volume. Okay, how do we do that? It is all the way up. There's nothing else I can do to make it louder. It's like the loudest it can be. Let's see. Advanced audio properties. Yeah, it's the loudest it can be. Maybe I can just just angle it a bit different. I put it like right in front of my face. Is that a bit better? Okay, I'm just gonna assume it's better. So we've got this hello world thing working, which is great. But the challenge we have now is we don't have any way of getting this string value from the Game Boy Core in a consistent way. So we're probably going to need to make a delegate, I reckon. So let's do that. And delegates are one of the things I always remember the syntax for. I don't need to look it up at all. What is the syntax for it? Delegate. Boop, boop, boop. There we go. Interface. Aha, protocol. All right. Let's call this Gameboy debug. Delegate. And then we don't have any optionals. We only have one, which is going to be update register debug with string. String. Okay. Then we need to store the delegate here. I think that's the right syntax, isn't it? Yes, perfect. Okay. So then our view controller is going to register as something that can handle that. We'll add mark Gameboy debug delegate void update. What did I call the method? Update register debug with string. Okay. Sweet. Then it's going to self dot debug output dot string equals string. Perfect. All right. That's great. And so we can do that. We can go like here, self.delegate, update string. This is coming from the Game Boy. Cool. Let's run that. It's not going to work because I didn't set the delegate. Doesn't run. And that's okay because I need to do this. Actually, I need to do it before we load the ROM. Self.gameboycore.delegate equals self. Then run it, and it should update that string. What? Why did that work? Load ROM, update register debugger string. Register debugger string. Register thing. Da 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 da. Delegate itself. Load ROM. This is the fun part of programming, right? Like things don't exactly work the way you need them to. Alright, it is stopping there. Maybe we don't have that view. Pure self.debug. Oh no, hang on. I know what it is. Because we're then setting it back after that. Oh boy. Alright, now it'll totally work. And it does. Awesome. This is coming from the Game Boy. Great. Cool. This thing always displays up there. It's annoying. Working. Good. Now, here's a challenge though, right? We don't want that to just show it once. We need that to show every time the registers change. And so we can't avoid it any longer. We're going to have to create our run loop now. So what should happen? When we call load ROM, we would expect that we'd store the ROM data and we'd chop it up and put it into whatever arrays we put it into and load all the memory and do all that initialization and display the test window and then I guess run the ROM, right? Like just start executing it. But we can't just start executing it because we don't have anything in place to do that. We don't have any mechanism to to loop over something. And the naive way to do that would just be to create it like an infinite loop and have it just run, through the instructions and that would work, but it would run like exceptionally fast, so fast that it actually wouldn't be valuable. And also, depending on the computer that you're running it on, the Game Boy would run faster or slower. So we need a way to regulate how fast it's going to run. So we can actually use SDL for that. So let's create a little method here called begin. Let's say begin emulation. That sounds fun. All right, I'm just going to call that here, begin emulation. We'll get rid of this delegate call. And here we're going to store a Boolean that's going to tell us whether or not we're running. And we're going to set that to true. And that way we can set that to false anywhere that we need to, and it will stop executing, which will be good. Otherwise we'll get stuck in an infinite loop. And then we're going to do a while loop. While is running, do something, right? The thing we're going to do is we're going to get an idea of how many ticks have passed by using SDL get ticks. All right, so if we look at the documentation for that, did it actually give us a documentation? Let's see. Get ticks. Gets a number of milliseconds since the SDL library initialization. Cool. And then let's get a reference to the event. Oh, actually, that's just creating a sample event. All right, so we need to poll the event to see if there's been any keyboard input, any controller input. So while, why is there a space there? It's ugly syntax. There we go. While SDL poll event, if event.type equals SDL quit. This will allow us to actually see if the user doesn't want to emulate stuff anymore. I think it's just wired to the escape key. If the user wants to do that, we'll call SDL quit. We'll set is running to false, and then we'll get out of this this loop here. And then once we get out of that loop, out of this while, then it will get out of here because is running will be set to false, and it will safely and keenly exit. So now we're just going to check event.type. We'll check for key downs and key ups. Key down, do something, and key up, do something. All right. So now we're still in this while loop. So now we're just going to make sure that we keep our speed regulated. So the way we're going to do that is, oops, divided by the frames per second. That's the frames per second minus ticks minus ticks. So this will be how long has elapsed since the beginning of this loop. And then if x is 0, then we're just going to delay SDL. Sorry, if x is greater than 0, we're then going to delay it by that many seconds, which means that it should evenly fire once every, well, 60 times a second, or 59.7 times a second. All right, so that's our little loop there. Pretty simple. In each of the loops, we should probably we need to do the fetch, decode, execute loop. But let's just make sure that we can run this and we can exit it. So what we should be able to do is run this, get the wrong one, run this one. Oops. Get the Game Boy screen and then hit escape, and it should exit. Okay. Or maybe quit. Maybe exit isn't the right, escape isn't the right key. Doesn't really matter. Put a break in here and see if it's running. Something's not working. Let's see. Do we not initialize the event somewhere? That's what it is. I remember this now. We need to do this. New thread with block is what it should be. There we go. Nope. Yeah, perfect. That's what it is. Yep. This does everything right, I think. This should run now. UI API called in a background thread. We can try this. Whoops, that's not helpful. Let's put a breakpoint in these ones here. And just for my sanity, let's get rid of become first responder. Okay, what's the problem here? Okay. UI API called on a background thread. Maybe that's fine though. Oh yeah, check it out. So when we hit up or down, it's then it is then recording that. So if we press a key, it's down. If we release the key, it's up, down, up, down, up, and so on 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 and so on. And so on. You can see that if you look in the bottom corner, which is covered by my face. Good idea. Let me do that. No, wrong one. There. So you can see just pressing the keys down, up, down, up, down, up, down, up, including escape. So escape isn't hooked up to quit, which is fine. We probably haven't mapped that key, but we can see that the loop is working because we can accept keyboard input. All right, very good. So let me put my dumb face back on. Very good. Although I might move. Let's keep it there. All right. So that's good because it means that it's regulating stuff. So we can now, like at the end of every one of these ticks, well, let's do this. Let's log every time we do one of these delays. Because I'm interested to see what X is every time one of these delays occurs. And I'll hide my face again because we'll be looking down at the bottom. Okay, so it's always 16, which I think makes sense because that's going to be where's my calculator? 1,000 divided by 60 is like 16, yeah. So that's going to be 1,000 divided by 59.7 frames per second, which is 16. So that's good. So that means that every time this delay occurs, a new frame is being created. So the perfect place to put this call to update the screen is going to be right here. Soft.delegate update register delegate. Now let's just do string format oops, ns date time interval since reference date. All right, kind of gross, but at least it'll update something that's different every time it updates. Except it crashed. Why did it crash? Because it's not a int, it's a float. There we go. Cool. So you can see that updating, it's updating 59.7 times a second, which is good, and that's exactly how fast we want the screen to update. What we want is like every time we get to that point, we want it to instead tell us what the contents of each of the registers are. So we'll get rid of that, and we'll say string get debug register string, and then we'll say self.delegate update self get debug string. Now, where are our registers? Let me put my face back on. There we go. Where are our registers? Okay, so string with format, percent ox2x percent I, and let's just go register dot reg. AF new line BC new line DE DE I new line HL percent I new line, and register AF register BC dot reg register de.reg register hl.reg. All right. Cool. Storyboard isn't big enough to hold it. There we go. Try that again. All right, cool. But they're not hex numbers, so let's format them to be hex numbers, and then let's show the individual contents as well. What is the syntax for? I think it's ox%x. Is that right? I think that's right. Okay. ox%x. Let me just try that one. Yeah, there we go, it's better. x, ox percent x, ox percent x. So that just that's just a format thing, just to make it look like hex numbers, really. Cool, but kind of unhelpful. So let's I guess let's split them out. So A, F, yeah, let's do that. So it'd be A, then F, ox percent x, oops, percent x, new line. Let's just see what that looks like. Now, I think it's high register af.low. There we go. And that's because of endianness with the Z80 processor. Very good. And then we'll do the same for B, C, D, E, and HL. Dot high, register BC dot low, register DE dot high, register DE dot low, register HL dot high, register HL dot low, and then we'll change this to be ox percent x, C, ox percent x, get rid of that, yes, yes, new line, D, ox percent x, E, ox percent x, H, ox percent x, L, da-da. Alright. Cool. How's that look, Fatima? Cool, and of course our little Gameboy screen, for whatever reason, always spawns up there, but there it is there. So that's that, which is good. Now let's actually see if it works. Okay, let's see if it's actually working. So what we can do after we call this at least once is let's change register AF dot high to what? To 5. Cool. And so we can see it's updated there, which presumably means that every time we update that, it'll automatically update as well, which is nice. Now we're missing two things, which is the stack pointer and the program counter. So we'll go stack pointer, ox percent x, and program counter, oops, new line, we'll not do the space there, new line, program counter, ox percent x, stack pointer dot reg, and program counter, which is just a word. Perfect. All right. Outstanding. We know that we set our stack pointer to that position because we have that here, oxfFFE, and our program counter we set to 100 as well. All right, so that's good. That's very, very good. Now let's get this stack pointer actually increasing. Okay. should we do this? I think what we should do is every time we're in one of these things, these delays, we should call a method which then does a frames amount of work. And so we should do that here. Let's do this. So we'll create a new method. Where the heck is it? Yeah. New method called update emulator. And we're just going to call that. Let's call it. Let's call it after we update the debug string. Yeah, let's do that. Okay. So we need to do a couple of things. We need to have a reference to the max cycles in a frame. And we need to know what the current cycles is. That's not right. Current cycles equals 0. All right. Then, while current cycles is less than max cycles, so while we can still do things in this frame, we're going to do what? We're going to do every time that this loop occurs, we're going to do a cycle of fetch, decode, execute. And what we're going to want to do, fetch, decode, execute, oops, E-C-U-T-E, we're going to want to return the cycle count. We're just going to return 1 as default. We're going to then get the current cycles, self, fetch, decode, execute, and then we're going to add that current cycles plus equals cycles. All right. So what this is doing is fetch, decode, execute is where we actually do all the work. It's where we take the current instruction that the program counter is pointing to, where we execute that instruction, and then where we return the amount of cycles that that instruction took. Because if we look at the instructions, let me go back to this manual. If we look at some of these instructions, we'll see this little column here, cycles, and so that represents how long each instruction takes in terms of cycles. So adding or whatever isn't just one cycle, there's actually a couple of cycles involved, and each instruction has a different count. Some are 16, some are 20, some are 8, some are 2, some are 0, some are hundreds. Actually, I don't think it's any of that hundreds, but they're all different. So we keep, we can't just say that each instruction is one cycle, because that's not true. We have to keep track of each of those individual ones. And so in our fetch, decode, execute switch, when we figure out what instruction we're going to do and we do it, we're then going to tell this update emulator method how long it took, basically. So once that's done, that's basically it. We then need to do a couple of things. We need to update the timing. We need to update the graphics. We need to check and handle interrupts. And then finally, we need to update the screen. All right. So we don't have any of these methods created just yet, so that's fine. Okay. So instead what we're going to do is So what we're going to do is just something really silly. Program counter plus plus. We're just going to increase the program counter. So each time this happens, we're going to increase the program counter. And what we should see is the program counter just going, just jumping up by 65,000 each time it updates. Let's see. Yeah, I suppose it's kind of working. It's just rendering what it can because it's a 16-bit number. But that is updating, which is nice. It means it's also refreshing fairly frequently as well, which is good. Okay. Oops. Very good. So we've kind of gone as far as we can without actually doing the fetch to code execute. So let's do that now. Basically, what we need to do is get the current instruction, figure out what it is, do it, return how long it took to do. So to do that, we're in fetch to code execute, and we literally just go word current instruction equals what did we call the memory? ROM memory. ROM memory program counter. Very good. Then we just do a switch on that current instruction. And we have a whole bunch of cases starting from the beginning of the instructions. So if we go back to our manual, and we go back to where the instructions start, that's registers, commands. So the first instruction is an 8-bit load. So here's the mnemonic for that, LDNN, N. The description is to put value NN into N. Use with, so NN could be either of these, and N is the 8-bit immediate value. So this is probably over 2 pages, no, it's over 1 page. So we've got a couple of different variants, 1, 2, 3, 4, 5, 6 different variations of this particular instruction. And each of those takes 8 cycles, and the opcode for each of those is 06, OE, 16, 1E, 26, 2E. So the easiest way to do this is we just go back to our switch, and we go if current instruction is 06. Now 06, so I'm just going to comment what they are. So this is LD, what is the thing? NNN. And it could be 06, OE, 16, 1E, 26, and 2E. These are the different variations. So to catch all of them, we want to do case OE, break, and then case 16, break, and so on and so on. It is actually this tedious. There's really no way to do it quicker. Case 1E, case 26, and case 2E. Break. Okay. But each of these is doing the same thing, right? It's taking the next, the immediate value, which is just the next number, basically, and it is loading it into one of these registers. So we could, for example, turn 0. Let's do this properly. So let's go cycles equals 0, and then we're going to go return cycles, And then we know that the cycles for these is 8. So we're just going to do that for all these. Perfect, because we know the cycles is always going to be 8 for those 6. And then all we need to do is just put a value into a register. So we can make a method for that. We can say load value byte value into register Can't use register because it is a reserved word, reg. And so the way we would use this one, 06 is going to be self load value byte. Now here's the tricky bit. We need to increment that program counter to get the next byte, but it's not as easy as just doing that though. There's a trick to it. Give me a second here. I'm just gonna guess. Beep boop beep boop beep. Load value, ROM memory, program counter plus 1. And that's gonna be B, so it'll be register BC dot high. And then we go program counter plus equals 2. All right. So we, oops, copy and paste each of these. So this one, OE is C. So it'll be low 1.6. And again, the way we're figuring this out is we're looking at our manual. And so 1.6 is the one we're interested in. And so that's D. And so that's how we're figuring out which register we need to use. So always be referring back to this manual. So 1.6 is D. So that's going to be register DE high. And 1E is E. So it'll be register DE low. 2.6 is H, so HL high, and 2E is L, so HL low. All right, so that is our load instruction. We'll go back to our CPU manual so we can look at it. So we've got all those there, the opcodes. It's only this table here, 06 OE, 16 1E, 26 2E, 8 cycles each go, B, C, D, E, H, L, you'll notice that A and F are missing from there, but that's okay. Not every instruction has every register. It's totally cool. But if we run this, we might actually see it happen. So let's run it. It's probably going to be a bit hit and miss because we're having the program counter increment in a really strange way. Yeah, I think it just gets stuck. That's okay. So let's see. Where are we? Where's my thing? Load ROM, begin emulation. Program counters there. Fetch decode execute. Program counter. It's just adding one at a time. To make it easier, let's just make this 20. That'll make it a bit easier. We don't have to wait so many loops. Because when this is actually working, we have all the instructions there. It'll be much better. But right now we're trying to do like just incrementing one at a time. Okay, why did that not work? We tried to update something in the background. It's all right. It might be the way we're trying to load. Yeah, because we never actually set the ROM memory or the cart memory. Yeah, that's right. We never actually do that, do we? So it's not actually accessing anything. The only thing we ever set is cart memory, but not ROM memory. Yeah, okay. So that makes sense. That's why that's probably not working. All right. So how do we do that? Let's have a look. Timers, LCD, opcode examples. Alright, we're not even using our read memory as well. We need to do that, don't we? So we made all those methods, we're not even using it. Self read from address, then program counter. There we go. Let's try that. Pinwheeling. Okay. Why is that pinwheeling? It's going to be one of these three returns. ROM memory. Just empty. Okay. Makes sense. We've got ROM memory here, which we're initializing. We initialize ROM memory up here as well. Here. That's okay. Let's just keep going. Oh, we should probably finish this up here. So we'll go equals by. It's really all it is. So the next instruction we'll do is this one, LD R1 R2. So put value R2 into R1. This one has quite a lot of different variations. So that's all of these here and all of these here. So this is like quite tedious, don't you think? But we have to go through and map out each of these. So we've got AA, AB, AC, AD, AE, AH, AL, AHL, and then B's, C's, D's, E's, H, L, and HL. So it's quite a lot of codes here. And the way we have to do it is one at a time. So, start a new one here, case, OX, which one are we starting with? 7F. And then we know that the cycles are going to be, for most of these it's 4, except the ones that deal with HL, and they're 8. So this one here is 4, and break. We know that we're going to increment the program counter, and we need our method, which is going to be what, put value into register, so we can use the same one. We're putting, in this one, we're putting A into A. Okay. So that actually doesn't make much sense, but whatever. So it'll be self load value into register. So we load value register af.high into register af.high. Not sure why that would ever be valuable, but there we go. Okay, case 7.8. Oops, hopefully I spelled case right. Can basically just copy and paste all of this and just change these values. So 7.8 is AB, so this will be register BC dot high. Then 7.9. 7.9 is AC, so this will be register BC dot low. 7A. 7A is AD, so it'll be register DE dot high. 7B is AE. Okay, so OX7B is register DE low. And AHL is the next one, which is OX7E. This one is HL, so we need to do register HL, but instead of high, it's .reg. That'll be the both. And also, this one is 8 cycles. And so you can kind of see, how long this takes. Like, it's just, you'll have a switch statement with 255 different variations in it. There are ways of optimizing it, but honestly, it's not worth doing it because this works. It's a bit tedious, but it works. And the optimization ones, they just become quite hard to to maintain if you're using like all these meta methods and stuff. So unfortunately, the simplest way to do this is just the tedious way. All right, speaking of tedious, we're up to B's now. So we've got case. Well, let me comment them here first. So we've got BB, BC, BD, BE, BH, BL, BHL. So they're the ones we have to play with. We don't have BA, which is interesting, but you know, it is what it is. And then we've got 40, 41, 42, 43, 44, 45, 46, 48, and just 46, I mean. So that follows a reasonable pattern there. So we can go case OX 40, and that's going to be BB. So I'll pop that in there, but it's going to be register B.high into register B.high. I'll copy this again. Case 41 is BC, so that'll be low. Oops. Case 42 is BD, so it'll be register D high. Case 43 is BE, DE low. 44 is BH. H.high. Then 45 is BL. Oops. And the last one is HL. So you'll notice that HL is used a lot. 46. When dealing with like a 16-bit number, that just tends to be the convention. Whenever you're dealing with like a 16-bit number, you use HL. So you'll find that a lot, that HL is the one that's always used like in parentheses. Just historical, who knows. But that's got 8 cycles. So that's the B's done. So now we've got the C's. So if we go back to our manual, the C's are 48, 49, 4A, 4B, 4C, 4D, 4E. So let's just do that now. CB, CE, no, CV, CC, CD, CE, CH, CL, CHL. So it's a bit confusing, right? Not really. It's actually quite simple. And then the opcodes for those are 48, 49, 4A, 4B, 4C, 4D, and 4E. All right. Case OX48. We can just copy this, paste it, but it'll be low into register BC.high. Copy that. Case 49. Oop, we need to change the cycles. There we go. We just copy that so we got the correct one. Perfect. 49 is CC, so it's BC low to BC low. 4A. Cool. A is CD. So register D high. For B is CE. I don't know why the light's going out. So that's cool. For B, it should be 4C. So 4C is CH. Register H high. 4D is going to be L. Register HL low, and then HL. For E, it's going to be HL. So register HL.reg, and we'll change the cycle count to 8. We're getting there. So what's next? Next we've got the D's. So it'll be 50, 51, 52, 53, 54, 55, 56. And that's it. So same as before. Don't worry, we'll have this code online so you won't have to type these out yourself. So it's DB, DC, DD, DE, DF, no, DH, DL, DHL. That's going to be 50, 51, 52, 53, 54, oops, 55, 56. Let me double check that. 56, yes. Yeah, that's right. So from top, case OX 50. We'll grab one of these. DB. So I got register there and register B high. I wonder. Nah, it's not worth it. I was thinking of a way to optimize this, but it's not worth it. The way I was going to optimize it is, instead of having to call all the time constantly, register bc.high, register bc.low and stuff, we could just have macros that represent, or type defs that represent the register we want. Reg B, Reg C, Reg D, Reg E, Reg H, Reg L, Reg HL, and then have the method itself figure it out. You know, if it's this, do this, if it's that, do that. All that would do though is make this line a bit cleaner, but let me think. Because how are we passing these? It's a primitive, so we're passing it by reference? No, passing it by value. Okay, yeah, we will have to do that. All right. Well, let's refactor it. So let's go to our prefix header, and we'll just make a quick type def enum. And this is just going to be reg A, reg B, reg C, reg D, reg E. Is that right? Yeah, so reg A, reg F, B, C, D, E, reg H, reg L. Then we need the pairing. So reg AF, BC, reg DE, reg HL. And we'll just call this registers. No, we can't call it that. We'll call it Gameboy registers. Okay. So then if we go back to here, we can make a new method. Basically, we can just reuse this one, but it would be Gameboy register. Gameboy register. And then it will be switch reg case reg A. Register a dot high equals value break, and then just that a million times. Reg f got low reg af dot reg. And we just do that for all of them. Get rid of that. So the next one is going to be B, C, BC. This will be register B. Good. Copy those. Then this will be D, E, D, E, D, E, D, E, D, E, and then HL, HL. H, L, HL. Register HL dot dot. Very good. Okay, so then this is gonna, all of these are gonna complain. Here's a problem as well. We need self read from address program counter +1. Here, these aren't erroring, but they're not right because it's not referring to anything, so we need to change these. BC is going to be reg B, and this will be reg C, reg D, E, reg H, reg L, reg A, reg B, reg C, reg D, HL, reg B, reg C, D, reg E, reg H, reg L, and so on. Tedious. Reg HL. C, reg D, reg E, reg L, reg HL. Nope. Missed one. Reg H. Reg H. Reg. Oops, daisy. Reg L. Reg HL. Okay. Reg B. Cool. So we're back on track now. And that's actually going to work because we weren't passing the references the right way. Oh, sorry, we weren't passing the primitives the right way, so it wouldn't have actually saved the value that we were setting it anyways. So at least this will work. Okay. So 51 is DC. Just one moment here. Okay. 51. DC. 51 is DC. So copy this. D into C. 52 is D. 53 is E. 54 is H. Nope. Okay. 55 is L. Nope. 56 is HL. All right. So back to our manual. What's next? E, 58, 59, A, B, C, D, E. So we've got 58. Oh, 58 is EB, EC, ED, EE, EH, EL, EHL, HL. And that is 58, 59, 5A, 5B, 5C, 5D, 5E. Okay. So we go back to this thing case, OX58. Oh, we've got to change this one to 8. Grab that. OX58 is EB, so this will be low, and this will be reg B. Copy that. Case OX59. 59 is going to be C. Case OX5A. 5A is D. 5B is E. Oops. 5C is H. 5D is L. And 5E, oops, that's right, is HL. You got it. 8. Alright, that's E's done. So nearly there. Back to the guide, we've got HL and HL left. So we got this. 60 to 66 is the H series. So it'll be HB, HC, HD, HE, HH, doesn't really do anything, HL, and that's going to be 60, 61, 62, 63, 64, 65, and 66. Now let's just map these out anyways, because we need to do them. LB, LC, LD, LE, LH, LL, LHL. And that's going to be 68, 69, 6A, 6B, 6C, 6D, 6E. Now you might notice a pattern here that all of the variations always are 0 to 0 to 5, 0 to 6, and then 8 to E. 0 to 6, 8 to E, and that's like the H, L, B, C, D, E. Ooh, chips. Awesome. So the last ones are the HL ones. So it's HLB, HLC, HLD, HLE, HLH, HLL, HLN. I wonder what that one is. HLN. Let's have a look. So we'll switch back to the manual. Now what could N be? Doesn't actually say there, does it? It says R1, R2 can only be A, B, C, D, E, HL, or HL. That's all it can be. But we've got one here that's HLN. So I wonder what that one is. Typically N's always the immediate value. Almost always. But in this instance it might be HL, HL because that would follow the pattern. And it would explain why it takes 12 cycles. So why don't we do HL, HL instead of HLN? Because that's probably going to make the most sense. So the HL opcodes are 70, 71, 72, 73, 74, 75, and 36. I know I just finished explaining that they follow a pattern and this one does not follow the pattern. So welcome to assembly. So let's do the H's first. Case OX60. So it's going to be HB. So we'll go register high into B. Oops, B. Copy that. 61 is HC. Six two is D. Oop. 63 is E. This one's H. This one's L. The next one is, you got it, HL. And that one's going to require more cycles. Alright, so now I got the L's. 6, 8. Let's grab this one here. Pop that one there. low. That's going to be reg B. Copy that. 69 C. Then 6A D. Yep. 6B is E. 6C is H. 6D is going to be L. And 6E is HL. And that's going to be 8 cycles. Now, the last one. I say the last one for this instruction. 70 is HLB. So let's get this one here. This is going to be HL reg, and this is going to be reg B, and 8 cycles is what's gonna do it. 71 is C. 72 is D. 73 is E. 74 is H. 75 is L. And 36, that's the tricky one, is HL. Now we don't know actually what this is. This one is HLN, but we're assuming that N is in fact HL. And that's 12 cycles. Alright, so that is the second instruction implemented. And so far we've got this really, really long switch statement, don't we? It's quite long. Okay. So the next instruction we're going to do, let's get back to our manual. The next instruction in the list is load AN. So put value N into A. In this instance, N is all of the registers, including all of the pairing of registers, including NN, including a pound sign. And NN is a 2-byte immediate value, least significant byte first. So the pound symbol, I think the pound symbol is, what is the pound symbol in this instance? I'm pretty sure the pound symbol in this instance is just, it's either anything or it's an immediate value. Let me see here. So I'm just looking through the manual as well, but I'm just looking with the physical copy because it's a little bit faster to flip through. What is the pound symbol? Or the hashtag symbol. I should say it. Is it the flag. No, it's not flag register. So I might just need to get some context cues here. See what hash represents in other places. I'm pretty sure it's just an immediate value. It is used a lot though, so I should probably figure it out. Okay, let's see here. Let's see if we can figure this out. Jump table. So what's an example of one that uses the hash? 3e. Okay. Add and carry was that. Add and carry. CE. Ah, okay. Hash just means nothing. Well, hash means zero it out.
Right.
Okay, helpful. Alright, cool. Well, that makes it easy, I suppose. It's a good thing we figured that out now as well. Alright, perfect. So we're just going to take a really short break, and then we'll be back very, very soon. So don't delay, don't wait, don't worry. We'll be back soon. Alright. And we're back. Crunch, crunch, crunch. Alright, where were we? Oh yeah, we're talking about instructions. So, the next set of instructions we're going to do is these ones, LDAN. They're very similar to, yeah, so the inverse of AN is NA. So if you can see here, LDAN put value N into A, and LDNA is put value A into N. So very, very similar, just the kind of inverse. So let's do that. See. Okay. So LDAN. LDAN. And we've got A, B, C, D, E, H, L, B, C, D, E, H, L, N, N, and hash. Okay. So we start with 7F. Now we're loading a value into a register, so we can use our method that we created, self load value. We have a duplicate of 7F anyways. So we don't need to do 7F. We can just go straight to 7.8. So 7F was implemented somewhere else. 7.8 is also implemented somewhere else, which is convenient. I think a lot of these are going to be implemented in other places. 7.9, yes. A, yes. B, C, D. I'm going to warrant a guess that B, C, and D are all done. Yes. C. Seven C is AH. Did we not do that one? Oh no, we did B and E. A, B, jump straight to E. Okay. So 7C and 7D will do. 7C is AH. So it'll just be self, load value. So this would be register that into, no, that's wrong. It would be load value register hl.high, oops, into register reg A. Cool. Program counter plus equals 2. Cycles plus equals, this one takes 4 cycles, and then we break. And then 7D is L, so same thing, except we're doing the low value. Alright. OA. So the next ones are OA, 1A, 7E. OA is ABC. ABC. So it'll do same thing, except it'll be register BC.reg into register A. The cycles are going to be 8 cycles. 1A is DE. Oops. 7E is HL. This one might already exist. Now the next, yeah, that one already exists, which is good. So the next one we're going to do is ANN, which is FA. This is ANN. Oops. So for this one, we need to get the next, the 2-byte immediate value. So we'll go word immediate equals self read memory from address, program counter plus 1. Is that right? I think that's right. That's gonna, is that gonna get us a byte or a word? That's gonna get us a byte. We need a word. I think there's a way to do it. Let me double check here. I think we need to do a join. FA. Yeah, it's just that. Just that. It's fine. Then we do what? Do some magic. Where's the magic that we do? Magic. Beep boop, beep boop, beep boop, beep boop, beep boop, beep boop, beep boop. Blah, blah, blah. We don't even need that. We can just do this. Grab that, pop that there, grab that, pop that there. 16 cycles, I believe, yes. And then the last one, 3E. This was the one, a pound. And this one is, we just load 0. 0 to stay. And it's 8 cycles. Yes. Very good. Okay. Good. So now we go back to our manual, we look at the next ones. So now we do it the other way around. So put value A into N. So this is the ones we're going to be doing now. Now we've probably done a bunch of these already, so let's see what we've got. So start from the top. 7F. I guarantee this one's already done. Yep. 47. Label it end of compound. 47. So we haven't got 47, which is nice. So 47 is BC. So we're putting A into B. So we'll go grab this here. This is LD NA or LDBC. No, B, A. A. So we're putting B into A. No, we're putting A into B. So it's going to be register dot high into B. Cycles is 4, so we'll just adjust that to be the right cycles, and we're good for that one. The next one is 4F, which is CA. The next one is 5-7. 5-7 is DA. So this will be D. The next one is 5F, and that is E. The next one is 6-7. If you do this enough, you start to notice patterns. So you'll notice the patterns are 7F, 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 7F. And that's probably intentional. Probably makes it a little bit easier for people to remember things, because, you know, we've got like the benefit of having a PDF on a screen in front of me, or a printed out copy of this, but when this was being used, they didn't have that. You'd have like an old dusty manual, or you'd have weird references and stuff. So like reference manuals and stuff. So presumably they used. Plus, you wouldn't have like methods like load value into register. You'd have to actually do it yourself. So, you know, I'd like to think that they made it follow patterns to make it easier. Now, who knows if that's true or not? It might not actually be true. It might just be that I'm trying to humanize something that is very tedious, but I like to think that it's because they wanted to make it a bit easier to remember. Alright, Reg A. Now these ones take 8 cycles. OX 1, 2. So this is going to be DE. Just grab this one here. Oops. There. DE 7 is HL. And then we've got NN. So that's going to be case EA. And this will be read from address, program counter plus 1. Yes. And that'll be 16 cycles. Okay. So back to our manual. That's all the A's done. So now we've got the next one, LDAC. Put value at address FF00 plus register C into A. Same as LDA FF00 plus C. Okay, so that one seems pretty easy to do. Let's do that now. So I think that's the end of the really long load ones. Yeah, so that's all the really long load ones done, and now it's just going to be weirdly manipulative ones, like OXF2. So this one we need to get a address FF00 plus register C. So we'd go self load value, then we go self read memory from address, and we go OXFF00 plus register C dot low into register A. Now I realize that we shouldn't be incrementing the program counter here. We should be doing it outside of the thing. I'm just going to keep doing it in these things, so it doesn't actually matter. But I think we should be doing the program counter increment outside of the fetch decode execute. But doesn't matter. Or maybe it does matter. Luckily, I can just do a find and replace. So let's just do that. Find, replace with that, I guess. Cool. Actually, let's just replace it with nothing. Don't want it to do that. It's fine. All right, cool. It's gonna make our formatting look a bit stupid, but that's fine. Okay, cool. So we'll do the program counter increment outside of the fetch decode execute, which I think probably makes the most sense. It has created a weird space, but that's fine. All right. So F2, 8 cycles. That's it. All right. So the next one, go back to our manual. Where's the mouse? Is LDCA. So we're putting A into address FF00 plus register C. It's basically the reverse of what we just did then. Not turn break. OXE2. Alright, so we're putting A into address FF00 plus register C. So that'll be self write memory with address, and then we'll go OXFF00 plus register BC.low, and then we'll do register high. Good. So that's that. And remember, when we're writing, we're using this method we created last time, this write memory with address, and that's gonna make sure that it's doing it safely. So it's not gonna write into places that it shouldn't be writing. That takes 8 cycles, plus equals 8. Okay, so back to our manual. Next instruction we're doing is this one, LDAHDL, same as LDDAHL, okay. LDAHL minus, all right, same as LDDAHL. All right, cool, so we've got them here. Put value at address HL into A, decrement HL. Okay, it's the same opcode, but it's got 3 different mnemonics for some reason, so that's fine. So we only have to do it once though. OX3A. So the first thing we've got to do is put value at HL into A. So it'll be self load value self read memory from address reg hl.reg into register reg A, then reg hl.reg minus Yep. 8 cycles. And break. Okay. I think that's probably where we should leave it. We've run over a bit of time, but that's okay. So we'll put this code up on our GitHub, which you can see here. Wait, which you can see. Oh, yeah, you can kind of see it there. And we'll be back next week to continue this one, but we'll also have another stream throughout the week at the end of the week. So look forward to that. Thanks so much for joining us. Make sure you check out oneflare.io and our YouTube channel, which is Oneflare R&D, and that GitHub repository and all the other public stuff we have as well. We have a cool ABN validation thing and some other stuff that we've made open source. So be sure to check that out, and we will catch you next time. Thanks so much. Bye. Bye.